welcome to physics class regarding the course wave optics. In today's session, we are going to see about the polarization of light. In the previous sessions, we have discussed about the interference of light in the first session, and in the second session, we have discussed about the diffraction of light. And in today's session, we are going to see what is the polarization of light. Okay, coming to the polarization phenomena. In this session, we are going to see about the introduction of polarization, and in the next session, we are going to see the how we can represent polarized and unpolarized light, and in the third content is about the methods to produce the polarization. What are the methods in order to produce the polarized light, or we can say plain polarized light, and in the next section we have to see about the Brewsters Law, then Malasla, what is double refraction. Okay, then we are going to see about the Nicoles Prism, how it can be constructed and how it can be worked. Okay, and then quarter wave plate, half wave plate, optical activity, what is specific rotation, and in the last we are going to see about the Lorentz half shade polarimeter. In that also we will able to see like what is construction, how it can be constructed, and coming to the action, how it will be worked. Okay, we will be seeing in this session. And coming to the first topic, introduction to polarization. Before going into this topic, let us see about what is light. As I have said that light is an electromagnetic radiation, right? Coming to light, in this session we are going to discuss about the unpolarized light as well as the polarized light. Unpolarized light is nothing but the ordinary light. So ordinary light consists of electric field as well as the magnetic field. Okay, they are perpendicular to each other. Both electric and magnetic field are perpendicular to each other and they are in phase with each other. Okay, also perpendicular, both electric and magnetic field are perpendicular to the direction of propagation. As in this diagram you can see that electric field and the magnetic field are perpendicular to each other. You can see that in x-axis magnetic field B is acting, and in z-axis electrical field E is acting, and so-called y-axis represents the direction of propagation. In this way they are perpendicular to each other. Coming to the polarized light, the transformation or transforming the unpolarized light into polarized light is known as polarization. Okay? Transformation of unpolarized light into polarized light is called as polarization, or we can say restriction of electric field vector. Okay, only electric field vector in a particular plane so that vibration occurs in a single plane only. Only electric field vibration will be seen in the polarized light. Okay, you can say that the polarized light have the characteristics of transfer wave. It will be having the transverse wave characteristics. Okay. Here you can see how a plane polarized light, in this diagram you can see after when you incident an unpolarized light on a polarizer, okay, then or the magnetic field component is vanished, only the electric field component emerges out. This is what the polarization means. Coming to the polarization, when an unpolarized light, okay, as ordinary light, you can say unpolarized light or ordinary light passes through certain crystals like tourmaline, okay, certain crystals like tourmaline, the vibration of light allowed will be having only one plane, that is electric plane, and in other directions the plane are cut off. Okay, you can see when an unpolarized light is passing through certain crystals like tourmaline, the plane of vibrations will be cut off in all other directions and it will be having only single plane. This is known as polarization. Or you can say that the light which has acquired the property of one-sidedness is called as polarization. In simple terms, you can say the light which has acquired the property of one-sidedness is called as polarized light. Now coming to the next topic, which is representation, how we can going to represent the polarized and unpolarized light. Okay, as I said, unpolarized light is nothing but the ordinary light. It will be consisting of very large number of vibration in all planes at right angles to the direction of propagation. Okay, this is how we are going to represent the, these are the two ways that we are going to represent the unpolarized light or ordinary light. But coming to the plane polarized light or polarized light, this is how we are going to represent. Vibrations are along only one plane. Okay, in the first diagram, the vibrations are parallel to the propagation of plane of the paper. Okay, the vibrations are parallel to the plane of the paper. And here you can see in the second diagram, it will represent that the vibrations are perpendicular to the plane of the paper. The first one represents the vibrations are parallel to the plane of the paper, and the second one represents the vibrations are perpendicular to the plane of the paper. Coming to the methods that how we can produce the plane polarized light. The first one is the polarization by reflection, which is called as the Brewsters Law. Then we can produce the plane polarized light by refraction, double refraction, selective absorption, and scattering. These are the 5 methods in which we are able to produce the plane polarized light. Coming to the Brewster's Law, or we can say production of polarized light by reflection. Okay, or you can say polarization by reflection, which is nothing but Brewster's Law. Okay. As I said, polarization by reflection is called as the Brewster's Law. Initially, Malasla observed the degree of polarization changes with the angle of incidence. Okay, the degree of polarization is changes with the angle of incidence. Brewster observed that for a particular angle of incidence, the reflected light is completely polarized. For a particular angle of incidence, the reflected light is completely polarized. Here you can say that P is the angle of polarization. This phenomena is known as Brewster's Law. In simple terms, according to Brewster's Law, we can say that the tangent of angle of polarization P is numerically equal to the refractive index of medium, which is nothing but mu. It will be represented mathematically like this: tan P is equal to mu, where P is the angle of polarization and mu is the refractive index of the medium. Brewster's Law also proved that the reflected and the refracted rays are perpendicular to each other when the reflected ray is completely polarized. Okay, when for a certain angle of incidence, for a particular angle of incidence, the angle of the reflected ray will be completely polarized. In that case, the reflected ray and the refracted ray will be perpendicular to each other. Okay, this is also concluded by the Brewster. Coming to the Malasla, it is about regarding the intensity of light. And completely plane polarized light from a polarizer is incident on the analyzer. The intensity of the light transmitted by the analyzer is directly proportional to the square root of the cosine of angle. The square root of the cosine of angle between the transition axis of the polarizer and the analyzer. Okay, here you can say OP is the plane of polarizer and OA is the plane of analyzer, and theta is the angle between them. Okay, now we know that intensity is proportional to the square of the amplitude. A is the amplitude of the incident wave, so intensity I is equal to square root of amplitude, nothing but A square. So I theta is equal to the I cos square theta, or you can say intensity of the polarization is directly proportional to the square root of cosine of angle of polarization. This is what Malasla determines us. And coming to the next topic, double refraction. When an unpolarized light, okay, when an unpolarized light falls on certain crystals like calcite, the reflected ray, okay, in this case, as I said, for certain crystals, when an unpolarized light falls on them, the refracted ray inside the crystal will be splits up into two parts. Okay, when an unpolarized light falls on certain crystals like calcite, the refracted ray which is emerges inside the crystal, it will be splitting up into two parts. One ray is called as the ordinary ray, which will be represented like O ray, and the other ray is called as the extraordinary ray, and the vibrations are perpendicular to each other. If the extraordinary ray is vibrating in such a way that its vibration is parallel to the plane of the paper, and ordinary ray will be having the vibrations in such a way that the vibrations are perpendicular to the plane of the paper. So here in this diagram you can see this is a calcite crystal. When an unpolarized light E falls on crystals like calcite, it will be splitting up into two parts. One is called as the extraordinary ray and the other one is called as the ordinary ray. The ordinary and extraordinary ray having the vibrations perpendicular to each other. This phenomena of unpolarized light splits into two refracted plane polarized light beams is called double refraction. Okay. This is how in general a calcite crystal looks like. When an unpolarized light falls on a calcite crystal, it will be splitting up into two parts as extraordinary ray and ordinary ray. This phenomena is known as double refraction. This is essential in the construction of Nicoles prism, this phenomena. Okay. Coming to the Nicoles prism, what the principle says us is that Nicoles prism is a device in order for the producing and analyzing the plane polarized light. We use Nicoles prism. Nicoles prism is a device for producing and analyzing a plane polarized light. It will be called as polarizer and analyzer. It will be used as a polarizer is nothing but a device which produces plane polarized light is called as polarizer, and the device which analyzes or which detects the plane polarized light is called as the analyzer. If no, first of all, we will see, as I said, in double refraction, when a light falls on certain crystals like calcite, it will be splits up into two parts inside the crystal. One is called as the ordinary ray and other one is called as the extraordinary ray. As this phenomena is known as double refraction. If by some means one beam is eliminated and the other beam is emerges out from the crystal, will be plane polarized light. Okay, if one beam is eliminated and only the other beam will be emerges out. Okay, only for the crystal will be plane polarized light. It will produces only one plane polarized light. In 1828, Nicoles eliminated the ordinary ray and he emerges out only the extraordinary ray by utilizing the phenomena of total internal reflection, a thin film of Canada balsam separating the two pieces of calcite. Okay. Coming to the construction of the Nicoles prism, a crystal is chosen in such a way that its length is 3 times as its width. Okay, its length should be 3 times as its width. Okay, the end faces of the crystals are grounded. The angle in the principal section becomes 68 degrees and 112 degrees instead of 71 degrees and 109 degrees. Okay. And in order to increase the field of view, the crystal is cutted into two parts by a plane perpendicular to the principal section as well as the end faces PR and OS. Here you can see PR and OS. Okay. In order to increase the field of view, okay, the crystal is cut into two pieces by a plane perpendicular to the principal section. Okay, by a plane perpendicular to the principal section as well as the end faces PR and QS. No, the two cut surfaces are grounded. Okay, these two cut surfaces are grounded. Here PSR and PSQ are the two surfaces are grounded and polished optically flat and cemented together by using a material called as Canada balsam. Why Canada balsam is chosen means the refractive index of Canada balsam lies in between that of the refractive index of the ordinary ray and the refractive index of the extraordinary ray. The refractive index of the Canada balsam lies between that of ordinary ray and the extraordinary ray. This is the reason why we have taken the Canada balsam material. Here you can see for sodium D lines, the refractive index of ordinary ray is 1.58 and refractive index of Canada balsam is 1.55 and the refractive index of extraordinary ray is 1.486. These are the refractive indices for sodium D lines. Coming to the action or working of Nicoles prism, when a light ray AB enters the faces PR, enters the faces PR in direction parallel to the long side, in a direction parallel to the long side. As you know that by the phenomena of double refraction, when a light ray enters a material like calcite, it will be splitting up into two parts as ordinary ray and extraordinary ray. Here AB is the incident ray. After passing through the crystal, at the B, the light ray will be divided into two parts. BO is called as the ordinary ray and the BE is called as the extraordinary ray. From the value of refractive index, we have seen that the Canada balsam is acting as a rarer medium for the ordinary ray. Canada balsam is acting as a rarer medium for the ordinary ray and denser medium for the extraordinary ray. It will be acting as the denser medium for the extraordinary ray. As we have know that the condition for total internal reflection is that the light ray should always travel from denser medium to rarer medium, and it is also mandatory that the angle of incidence should be greater than the critical angle. It is compulsory that the angle of incidence should always be greater than the critical angle, and the next one is that the light ray should travel from denser medium to rarer medium. Now I am considering the case of the ordinary light. As you know that the Canada balsam is acting as a rarer medium, which means that the ordinary light will be acting as a denser medium. We know that when a light ray travels from a denser medium to rarer medium, in which the angle of incidence is greater than the critical angle, so the ordinary ray is completely reflected at the Canada balsam surface by the phenomena of total internal reflection and is absorbed by the tube containing the Nicoles prism. Only the emerger E ray, or you can say the extraordinary ray, will be emerges out, in which this plane of emerges out as the plane polarized light whose vibrations are parallel to the plane of the paper. Only the extraordinary ray emerges out and the ordinary ray is reflected at the boundary. Now coming to the uses, as I said earlier that the Nicoles prism is used as both polarizer and analyzer. Now when two Nicoles prisms are placed which their principal sections parallel to each other, with their principal sections parallel to each other, as we know that at the Nicoles prism the ordinary ray emerges out here, you can see. Then only the extraordinary ray whose vibrations parallel to plane of the paper is transmitted by one and is freely transmitted by the other as well. In this case you can say that the first Nicoles prism N1 is acting as the polarizer, while the second Nicoles prism is acting as the analyzer. One is producing the plane polarized light and the other one is detecting the plane polarized light. This way you can say that the Nicoles prism will be acting as both polarizer and analyzer. If the second prism is gradually rotated, then the intensity of the extraordinary ray gradually decreases. When the two Nicoles are at right angles to each other, that is, they are crossed position. Here you can see in the B diagram, you can see when they are in crossed position, no light comes from the second prism. When extraordinary ray enters the second prism, it acts as ordinary ray and is totally internally reflected. In this case also we can say that the Nicoles prism is acting as both polarizer and analyzer. N1 is a polarizer and N2 is a analyzer. N1 is producing plane polarized light and N2 is detecting the plane polarized light. Now coming to the next topic, quarter wave plate. What does mean a quarter wave plate? When a calcite crystal is cut with optical axis parallel to the surface, As you know that when an polarized light whose vibration parallel to the plane of the paper enters into this calcite crystal whose optical axis cutted parallelly, okay, it will split up into ordinary ray and extraordinary ray. They will travel along the same path but will different velocities. The ordinary and extraordinary light will travel with different velocities. The velocity of the extraordinary ray is greater than the velocity of the ordinary ray. As a result, a phase difference is introduced. If the thickness of the crystal is such that it introduces a phase difference of pi by 2 or a path difference of lambda by 4, okay, between the ordinary and extraordinary rays. Okay, what? Phase difference of pi by 2 and a path difference of lambda by 4, then that instrument is called as the quarter wave plate. Here you can see mu naught is the refractive index of the ordinary ray and T is the thickness of the plate, and mu e is the refractive index of the extraordinary ray and T is the thickness of the plate. Okay, as I said that in quarter wave plate the refractive index for the extraordinary ray as well as the ordinary ray, the velocity of the extraordinary ray will be greater than the ordinary. Here, in order to find the thickness of the quarter wave plate, the formula is given by T is equal to lambda by 4 into mu naught minus mu e, where lambda is the wavelength of the incident light and mu naught is the refractive index of the ordinary ray and mu e is the refractive index of the extraordinary ray. Now coming to the half wave plate, it is also similar to the quarter wave plate, but if the thickness of the calcite crystal plate cut with its faces parallel to the optic axis in such a way that it introduces a phase difference of pi. It introduces a phase difference of pi or a path difference of lambda by 2. In quarter wave plate, it will be lambda by 2 and pi by 2 and lambda by 4. But in case of half wave plate, the phase difference is pi and the path difference is lambda by 2. The thickness of the crystal in order to find is given by T is equal to lambda by 2 into mu naught minus mu e. Similarly, where T is the thickness of the plate, lambda is the wavelength of the incident ray, mu naught is mu 0 or mu naught is the refractive index of the ordinary ray and mu is the refractive index of the extraordinary ray. Now coming to the next topic, optical activity. When a plane polarized beam is passed through certain substances, the plane of polarization of the polarized beam is rotated through certain angle. Its rotation will be changed. This phenomena is known as optical activity, and the substances which produces this activity are known as the optically active substances. Okay, the substances which produces the optical activity are called as the optically active substance. The examples of optically active substances are sugar crystals, sugar solution, or quartz, etc. If the plane of vibration is rotated in the right side, which means in clockwise direction, that materials are called as dextrorotatory. If the plane of vibration rotated anti-clockwise, those are called as the levorotatory substances. Now coming to the specific rotation, at a particular temperature and for a particular given wavelength, the specific rotation, which is S, is defined as the angle of rotation, which is theta, of the plane of vibration of polarized light produced by 1 decimeter length of its solution when the concentration is 1 gram per cubic centimeter. It is given by formula S equal to theta by L into C, where S is a specific rotation, theta is the angle of rotation, L is the length of the solution in decimeter, and C is the concentration or the strength of the solution. This is the formula for specific rotation. With this, we are going to see how a Lorentz half-shade polarimeter will work. Coming to the Lorentz half-shade polarimeter, it is in order to find out the accurate measurement of the angle of rotation, which is theta, of the plane of polarization of a plane polarized light. Okay, in order to find out the angle of rotation, we will use this polarimeter. Okay, and also in order for the calibration to read directly the percentage of the cane sugar in a solution or the strength of a sugarcane solution, they are named as saccharimeters. Coming to the construction of a Lorentz half-shade polarimeter, the schematic diagram of Lorentz half-shade polarimeter is shown in this diagram, where S is a monochromatic source of light, falls on a convex lens cell. After passing through the convex lens, the light rays will become parallel. Okay, here N1 and N2 are the two Nicoles prisms, where N1 is act as polarizer and N2 is acting as the analyzer, where HS is a half shade and T is the tube, SC is a graduated scale, circular scale, and T is the telescope. Here N2 is capable of rotating about the common axis of N1. Okay, N2 is about rotating while the N1 is fixed. As I said, N1 is a fixed Nicoles prism while N2 is a movable Nicoles prism. Its movement can be calculated by using a graduated circular scale. The plane of polarized light now passes through the half shade and then through the tube T. Tube is a hollow tube here. T is a hollow tube containing the optically active substance like sugar solution like that, and it will be having larger diameter at the center so that no air bubble may be in the path of the light when filled with liquid. Okay, the telescope is focused to the half shade Hs. Okay, now when a polarized light falls on a lens, the light rays becomes parallel and it will be passed on a polarizer, then passes through the half shade and tube, and it falls on the analyzer. After passing through the polarizer, the light ray will becomes plain polarized light and the analyzer will detect, and it will be seen in the telescope. Now coming to the working or the action of a Lorentz half shade, here you can see in the telescope it will be look like this. Here ADC is the quartz part, ADC is the glass part and ABC is the quartz part. Okay, so it introduces a phase difference or phase change of pi between the glass part and the quartz part. These two plates are cemented along the diameter AC. The thickness of the plate is so adjusted such that it absorbs the same amount of light as the quartz plate. Okay, the thickness of the glass plate is adjusted so that both the quartz plate and the glass plate will absorb the same amount of light. Now, let the plane polarized light from the Nicoles prism N1 is incident on the half shade along the PQ. Here in this diagram you can see along the PQ. So which makes an angle theta with the AS. The ordinary, here you can see the ordinary component is OM and the extraordinary component is OL. As you know that as the quartz wave plate serves as a half wave plate which introduces a phase difference of pi, which means that the ordinary component changes from OM to ON. So the new component of ordinary light is ON and the extraordinary component is OL. The resultant component of the extraordinary and ordinary component is OR, which makes an angle theta with the XY dash plane. Now, the half shade serves the purpose of dividing the field of view into two parts. If the plane of analyzer N2 is parallel to the PQ, then the glass part will appear brighter than the quartz position, which means that the light ray will be uninterrupted or unobstructed in the glass part and it will be obstructed in the quartz part. If the plane of analyzer N2 is parallel to the RS, here you can see in this diagram RS, then the quartz part will appear brighter than the glass portion, which means that in glass portion it will be obstructed and in quartz position it will be unobstructed. If the plane of polarizer is parallel to AS, then the field of view is equally brighter in glass as well as in quartz. With this we will be determining the specific rotation S. You can see that the tube is filled with, initially it is filled with a distilled water and the telescope is focused to the half shade. The analyzer is rotated to get both the halves equally brighter. The readings are noted from the circular scale. Okay, now the distilled water are replaced with the optically active substances like sugar solution. Then the telescope is focused for half shade. The analyzer is rotated to get both the halves equally bright. The reading is noted from the circular scale. The differences between the distilled water's reading and the optically active substance reading will use the value of theta. Now from the experiment this experiment is repeated for different concentrations of the solutions. By changing the concentration of the solutions, a graph is plotted between the concentration of solution on x-axis and angle of rotation on y-axis. It will be a straight line passing through the origin. The ratio of theta by c is determining from the graph. The length of the tube is measured directly. So by substituting the values of theta, angle of rotation, length of the tube and concentration, we will be able to find the specific rotation. With this formula, we can able to find out the strength or the concentration of the solution by varying this. C is the concentration of the solution, which is given by theta by L into S. In this way, we can able to find the specific rotation or the concentration of the given optically active solution. This is called this instrument which is called as the Lorentz offset polarimeter. With this, I am concluding the session. Thank you all.